Okay, good morning, everyone. Continue our discussion of chapter 6. First, we'll look at transfer functions. We can solve the example using a transfer function. The homework that is due tonight, actually, like 15-20% of the class across all sections have actually completed the homework. It's only one problem, one short answer question, and the problem that we're about to do in class would be exactly the same as the one that's in the homework. Okay. So let's go ahead and do that. And then we'll introduce filters and talk about those circuits, and then be an example at the end of those filter circuits also. So class notebook, let's see. All right, we stop here. We'll introduce the transfer function. H of f, transfer function, is describing the behavior of a circuit as a function of frequency. It is simply the ratio of the output voltage to the input voltage. Is a dimensionless quantity, no units. It's simply the ratio. It's simply describing how the input is being transferred to the output by that circuit. We don't know what is inside the circuit. We don't care how it does it. We only need to know what it does, so we can predict the output. Okay. So here is an example where you are given a input, and that input, sorry, not the input, the transfer function of this network or the circuit is given in graphical description. There are two charts. The one on the left gives you the magnitude. The one on the right gives you the phase. Also made the point that V out and V in are phasors, complex quantities. So H of f, the transfer function, is also a complex quantity. So it has magnitude and it has phase. So in this particular problem, we are simply given the transfer function in graphical form, and we are asked to find the output for any given particular input. Okay. So let's take a look at the input first. What do we see? There are three components to this input: V in 1, V in 2, and V in 3. If you think back to chapter 5, what is required if we need to add or subtract two or more sinusoidal functions? Same frequency. The frequencies must be the same. If the frequencies are not the same, we cannot add or subtract them. So as we look here, three components: 3 plus 2 cos 2000 pi t plus 4, or not 4, plus cos of 4000 pi t. The frequency for all three components is separate, and hence we cannot combine them. So in general terms, the plus sign that you see in this equation here is simply illustrating and, the word and, A and D. That's all it is. It's like, oh, it's V in T is comprised of V in 1 and V in 2 and V in 3. It could be hundreds of components, or simply be and. So in this case, that plus sign is simply indicating 3 and 2 cos 2000 pi t and cos of 4000 pi t. That's all. That plus doesn't mean anything in this case. Okay, it's all these components coming into the circuit all at once. Yes. Yes. Yeah. So it's a real life example. The first one is let's say the first one is a signal from Verizon. Second one is a signal from AT&T. Third one is a signal from T-Mobile. Right? If I hold up my cell phone right now, it's going to pick up wireless network from, from the campus Wi-Fi. It's going to pick up the cell phone signals from different. So it's all components coming in. We are just saying and, like that's all it means. Doesn't mean anything else. There's no mathematical, there's just a mathematical representation, but it doesn't mean anything we can do about it. Okay, so we have three quantities, V in 1, V in 2, V in 3. We extract the information about the frequency in hertz because our charts are given as a function of frequency in hertz. Okay, if they were given in omega, we would need the information for omega. Omega is 2 pi f, right? Omega is 2 pi f. So we compare this with our standard expression. V of t is Vm cos of omega t plus theta. We compare all three components with that standard expression. What do we get? For V in 1, it's one single value, 3 volts. There's no frequency information. There's no time dependency. It's not a function of time. So V in 1 of t is not really a function of time. It's a flat line at a value of 3 volts. Right? It's basically a DC component. That's all it means. And so the frequency of that is simply 0 hertz. Frequency of the first one is 0 hertz. Excuse me. So if it's simply a number, there is no time dependency, and it's simply 0 hertz. Yes. Yeah, this is given. Find V out of t if V in of t is. Then we do the same for the second and the third component. So V in 2 and V in 3, we equate omega, and we find the value for f. So f2 is 1000, f3 is 2000. And that's all. Find frequency information f1, f2, and f3. At the same time, we can write out the phasor form for V in 1, V in 2, and V in 3. Okay, phasor form for V in 1, V in 2, and V in 3. Since the first one is simply a flat line at 3 volts, no phase angle is 0. V in 2 is a vector. The angle for that is still 0. Third one is 1 with an angle of minus 70. Minus 70. So far, so good. Any questions? Okay, then we take our frequency information, we go over to our chart. What do we see? This is 0 right here. So this is 1, this is 2, and this is 3. Right? Value 1, 2, and 3. Same thing here. This is 1, 2, and 3. Those are the values that we need. Okay, h of f is described graphically. We simply need to determine how that circuit behaves at that given frequency. And we obtain the information from those charts at those 3 points, f1, f2, and f3. From f1, f2, and f3, we extract the values for the magnitude and phase of h of f. So f1, f2, f3 are 10, 100, and 1000. Oh, sorry, not 10. Mixing up two problems. 0, 1000, and 2000. So f1, f2, f3 are 0, 1000, and 2000. We find the value of the magnitude and the phase at those 3 frequencies and directly write down the transfer function at those 3 frequencies. So h of 0, h of 1000, and h of 2000. And that's what we have noted down here. Okay. Let's take a 10-second pause. Think over that. Let me know if you have any questions. Yes. So question being asked is where? So left side is the magnitude, right side is the phase. So you're obtaining the values from those two charts. H of 0, of course, angle is 0, no change in the phase. Only the magnitude is changing. Okay, only the magnitude is changing. Now, H of F is the ratio. Oh, any other questions? H of F is the ratio of output voltage to input voltage, V out or V in. Transform the equation, we can predict what the output is going to be by simply multiplying the transfer function with the input, H of F times V in. And then we calculate and find the output. So V out 1 is simply given by H of 0 times V in 1. V out 2 is H of 1000 times V in 2, and V out 3 is H of 2000 times V in 3. Simple multiplication. And then we find the output. The point being, we don't know what the circuit is, we don't know what the circuit does, yet we can still predict the output because we know the transfer function. So think over everything. Let me know if you have any questions. And I will recap the procedure again. All right. Any questions? Okay, I'll do a recap. We are given the transfer function. The transfer function of a circuit is being described graphically in two charts. On the left, we have magnitude. On the right, we have phase. X-axis is frequency in hertz, meaning it's given as a function of frequency f. We are asked to find the output V out of t if a given input V in of t comprised of this expression. When we look at the expression, we can see it has three components. Those three components can be separated out. The frequencies are all different, so we cannot combine them. So V in 1, V in 2, V in 3. Now, transfer function describes the ratio of the output to the input. So we can predict the output or calculate the output by simply multiplying H of F with V in. H of F and V in at any particular frequency. And so we need the frequency information. So the first step, we determine the three frequencies, 0, 1000, and 2000. And once you have that, you write down the phasors for the input components. And then we take the frequency information over to our charts, and we extract information about the transfer function at each one of those particular frequencies. So then we have three values for H. H of 0, H of 1000, and H of 2000. Once we have those, we simply take the phasors and we multiply it together, and we have our final output. Three quantities, the frequencies are still the same. The frequencies do not change. They are not affected. And so the final answer, when we perform the inverse phasor transform as a function of time, all three separate quantities, it's 12 and 6 cos of 2000 pi and 2 cos of 4000 pi. Mathematically, we write it with a plus sign. And that's your final answer, V out of t. Do the steps make sense? Yes. Those are provided. Those are provided in the question. So question being asked is where these graphs come from. So the graphs are provided. So it's part of the problem statement. So the graphs are provided. and the input V in of t is also given, and we are asked to find V out of t. How long do you think it would take you to solve this? 7, 8, 10 minutes, 15 at the most? That's the homework. So the point being, if you have time right after this class, take 15, 20 minutes and knock it out. Okay, so then let's go into filter circuits. In filter circuits, we're going to use the component behaviors at extremely low and extremely high frequencies. So this is what I like to call a handy dandy table. This handy dandy table will allow you to analyze any kind of filter circuit with a very quick and easy analysis, or at least a rudimentary analysis. All we are going to do in this quick and easy analysis is see whether we have V out or not, depending on the value of the frequency. So the two values are when F tends towards 0 and when F input frequencies tend towards infinity. We know capacitors and inductors behave differently at different frequencies. ZL is J omega L or J 2 pi FL for an inductor. Impedance is directly proportional to the frequency. For a capacitor, ZC is 1 over J 2 pi FC. ZC is inversely proportional to frequency. Meaning as the frequency increases going towards infinity, the impedance for an inductor increases. It behaves like an open circuit. At low frequencies, inductor behaves like a short circuit. Capacitor is the exact opposite. Behaves like an open circuit at low frequencies, behaves like a short circuit at high frequencies. And we know this from chapter 3. Remember, DC steady state. DC steady state. Capacitor is open, inductor is short. Zero frequencies mean DC steady state. Okay. So based on this handy dandy table, we can analyze any circuit. Okay. In the filters we're going to study, we'll have capacitors and inductors, and of course resistors. You cannot build an electric circuit without a resistor. Okay. Resistors are one of the indispensable components. Okay. So the filters we're going to study in this class or in this chapter, broadly classified between capacitors and inductors. So we can describe them as RC or RL. And depending whether they are blocking or passing a certain band of frequencies, we can call them as low pass filters or high pass filters. So this low pass and high pass is referring to frequency. Again, remember, we have all these frequency signals all around us. We want to filter some of them out, meaning something with a particular band of frequencies or low frequencies are either passed or blocked. And so based on that, we have RC, low pass filters, high pass filters, and we have RL, low pass and high pass filters. Then we have band pass and band stop filters. Okay, band pass and band stop filters. If you have one energy storage component in your circuit, you require a first order differential equation to solve for the quantities. Hence, we refer to it as a first order circuit. Same thing with the filters. If you have one energy storage element, meaning one inductor or one capacitor, then it's a first order filter. If you have more than one, second order, third order, fourth order, so on and so forth. Okay. Filters and filter design is an entirely different specialization within electrical engineering. Okay, there are high-level classes we take that that go through the entire topic. Of course, that's not something we do here. Even EE students don't look at those until they get to the junior or senior level. So based on that, let's look at our first circuit. Okay, this is a RC low pass filter. Of course, it states so in the title, but let's take a look at what this circuit is actually doing. So we have a resistor and a capacitor. And if you look at the circuit, what do we see? You have a voltage source and a resistor and capacitor in series. Again, going back to chapter 1, just because there is a open terminal connected, or you see a connection at that junction, does not mean that they are not in series. There is no component. Those terminals that you see simply indicate you're taking the output across the capacitor. Okay, simply taking the output across the capacitor. But fundamentally, the resistor and capacitor are in series and they're connected to a single voltage source, Vin. Okay, Vin. So you have R, you have C. The current flows in this direction. I. Point of entry is plus, point of exit is minus. In this circuit, the output is taken across the capacitor. So let us analyze using our handy dandy table whether this functions as a low pass or high pass. Okay, obviously the title is already in there, but let's see how we can do that. As F tends towards 0, capacitor behaves like an open circuit. Low frequencies, capacitor behaves like an open circuit. So circuit looks like this. Output, yes or no? What do you think? Output, yes or no? What is V out? You're giving V in, you have a resistor connected to V in, and you're measuring the voltage directly at that point. What do you think? Someone says 0. Anyone else? Take a shot at it. What about F is equal to infinity? Capacitor behaves like a short circuit. What is V out now? This is 0? Yes, it is, because you're taking the output across the same node. If you measure voltage across a short circuit, V out would be equal to 0. Voltage would be 0. So at higher frequencies, capacitors behave like a short circuit. Output voltage would go towards 0. Here, whatever voltage is applied by V in, we obtain at the output. So V out would be equal to V in. It's simply a resistor connected in series with a voltage source. Because no current is flowing through there, voltage is the exact same as the input, both ends. So quick and easy analysis is performed in this manner. More often than not, you'll always see a component shorting out the output terminals. Simply, if that happens, then you simply state V out is equal to 0. So F is equal to 0, meaning low frequencies, you obtain output. High frequencies, no output. Low frequencies are allowed to pass through. High frequencies are blocked. Hence, it works as a low pass filter. That's the quick and easy analysis. No circuit analysis, no calculations, no concepts, no theory. You simply model the circuit, model the capacitors and the inductors at F is equal to 0 and F is equal to infinity, and then look at the output. Is V out yes or no at F equal to 0? And then again at F equals to infinity, is V out yes or no? That's it. Okay. So it is a low pass filter, LPF. We use these acronyms a lot in electrical engineering. Okay, LPF and HPF. Okay, there is a derivation. Derivation is rather straightforward, but again, we don't usually do that for 201. If you can find I by applying Ohm's law, V over ZEQ. ZEQ is R plus ZC, and then output V out is the capacitor voltage VC, which you can find from I times ZC. Okay. These are all phasors. These are all complex numbers, complex quantities. You will have V out and V in that equation. You rearrange the terms to obtain V out to V in, which would give you H of F. After rearranging the terms, we would obtain H of F as 1 over 1 plus J F over FB. Okay, 1 plus J F over FB. But yes, low pass filter. Okay, so here on the right side, is this the question? So how did we conclude that it's a low pass filter? We model the capacitor at F is equal to 0. At F is equal to 0, capacitor behaves like an open circuit. If it's open circuit, whatever input we give is going to appear at the output. In this case, if it's open circuit, there's no current flowing through it. The voltage V in appears at the output as it is, right? V in appears at the output as it is. You're simply connecting, think of it in this terms. You have a voltage supply, you're simply measuring the voltage at the output terminals. No current flowing, so the resistor is not doing anything. And then, in this case, because it's a short circuit, if you measure the voltage across a short circuit, output voltage is always going to be equal to 0. Because voltage across a short circuit, there's no difference in potential, output will always remain 0. Yes. Yes. We treat the capacitor as either open circuit or short circuit, and we simply look at how the circuit is behaving, whether we obtain output or whether we don't obtain output. So at low frequencies, we obtain output, hence it's allowing the low frequencies to pass through, so it's a low pass filter. At high frequencies, the output is blocked, output goes to 0. It's blocking high frequencies. So it's a low pass filter. All right, any other questions? Let's take a pause, think on that. Let me know if you have any questions. Yes. Because there is no current flowing through the, so the question being asked is, why does this resistor not affect? It's open circuit, no current flows through it. So voltage at both ends is exactly the same. Yes. No. That's the exact same circuit. We're just analyzing the same circuit. These are the same. This is the same. There's no difference. You're simply replacing the capacitor with either a open circuit or a short circuit, depending on the input frequency. So if the input, if V in has a frequency value that is low, then the capacitor behaves like an open circuit. If V in has a frequency that is high, then the capacitor behaves like a short circuit. So all four circuit diagrams are exactly the same circuit. There is no difference. It's only the behavior of the circuit that changes because capacitor impedance changes with respect to frequency. We are simply modeling the circuit at low and at high frequencies. Does that answer your question? Sort of. That's a very good question. So the question being asked is, what do we consider as low and what do we consider as high? A very good question. That depends on the application and the purpose. If you're talking about audio frequencies, then let's say even 10 kilohertz is considered high frequency. Okay. If you're talking about like mobile communication, 10 kilohertz is nothing. Right? And the first slide I pointed out, AM radio stations transmit at 600,000 hertz. FM radio stations transmit at 101 megahertz. So compared to those frequencies, 10 kilohertz is low. But compared to human hearing range, 10 kilohertz is considered high. So the answer is that what is low and what is high depends on the application. Okay, depends on the application. All right, other questions? As new concepts, it will take some time to get used to, especially because we are blurring the lines between like circuit analysis as individual voltage and currents, and then looking at the system as a whole. So in this case, we want to kind of transition away from circuits, not circuits, but transition away from voltages and currents, individual voltages and currents, and think of it in terms of like an input coming in, circuit transforming the input, and then we're just getting the output, rather than some voltage or current moving through the circuit. Voltage or currents moving through the circuit is what allows us to actually define the output transfer function. So here, as I was saying, V out over V in can be derived from the voltages and currents. But once we have the V out and V in equation, which is shown here, we can directly determine what the output would be, no matter what the input is. Okay, once you have the transfer function, you can simply plug in different values of the frequency, and you can predict what the output is going to be. Okay, and that's the purpose, that's the point. When you solve that equation, you obtain 1 over 1 plus J F over FP. The transfer function will change the magnitude and will change the phase of the incoming signal depending on the behavior, depending on the frequency of the incoming signal. Hence, it is a function of frequency, H of F. H of F, a function of frequency. So the F over FB, F is the variable of the input frequency. Similar to the example problem we saw where you had 3 components with different frequencies. There's another example where you'll see a component with an input signal with 3 different kind of frequencies. Okay. FB is a constant. It's a constant that is defined by this equation, 1 over 2 pi RC. Depends on the values of the resistor, depends on the value of the capacitor, 1 over 2 pi RC. Okay, and that is fixed. That break frequency is what defines where the frequencies are allowed to pass through and which frequencies are blocked. Okay. All frequencies below the break frequency will be allowed to pass through. All frequencies above the break frequency will be blocked. So if we plot out a chart with a normalized transfer function, break frequency FB, so over here is a normalized transfer function. If it was an ideal filter, we could say for a low pass filter, this is FB here. All frequencies below break frequencies are passed. All frequencies above are blocked. When we say pass and block, it means we are taking the signal, which has, let's say, 5-volt signal or 10-volt signal, and at the output, you get 0 volts. That means it's blocked. If you send in 10 volts and you obtain 10 volts at the output, it means you're passing, you're allowing it to pass through. Okay. The amplitude or the magnitude drops. So anything below is passed. This is passed. And this is blocked. Hence, it works as a low pass filter. Okay. The output amplitude or the voltage level drops. All right, questions? Oh. Excuse me. Break frequency is also known as cutoff frequency FC. Other classes and some books also use omega. So omega C would simply be 1 over RC. Omega is 2 pi F. So if F is 1 over 2 pi RC, then omega is 1 over RC. 1 over RC. Now, instead of taking the output across the capacitor, what if we take the output across the resistor? In that case, you obtain a high pass filter. Circuit is exactly the same. It's not changed, except the output is now across the resistor. It's still a series circuit. We are drawing the schematic with the capacitor in place of the resistor, but it's still the same circuit. Electrically speaking, it's the exact same circuit. There is no difference. We are simply taking the output across the resistor. That is all. It's still a resistor in series with that capacitor. Okay. So plus minus, and the output is now across the resistor. If you use the same handy dandy table and model the circuit at low and high frequencies, this is what you'd obtain. At low frequencies, capacitor again behaves like an open circuit. So you have V in and V out. And at high frequencies, behaves like a short circuit. So what happens at high frequencies? Are we getting an output? Yes or no? Second diagram. At high frequencies, capacitor behaves like a short circuit. Output yes or output no? I see some nods and I see some shakes. You're overthinking this. Output is yes. It's a short circuit. You're simply connecting the output directly across that voltage supply. Taking the output across the resistor means taking the output across that voltage V in. So yes, we do obtain an output. How about low frequencies? Nothing. There's no current flowing through the circuit. So output V out is equal to 0. V out is equal to 0. So low frequencies are blocked and high frequencies are allowed to pass through. Hence, it works as a high pass filter. Works as a high pass filter. The important point is it is still exactly the same circuit. We have not changed anything about the circuit. The only thing that is changed is where we are taking the output. So the point being, the same circuit functions as both high pass as well as a low pass filter, depending on where you take the output from. Okay, so depending on where you take the output, it behaves as a high pass or a low pass. The transfer function for high pass is different. The denominator is the same. The numerator, you have an additional component, JF over FB. JF over FB. The break frequency equation, however, remains the same, 1 over 2 pi RC. Okay, 1 over 2 pi RC. All right, questions? Okay, let's look at RL filters then. If you replace the capacitor with an inductor, and you still take the output across the resistor, you get what is known as a RL low pass. RL low pass. F tends towards 0, inductor behaves like a short circuit. You get a similar circuit to the first one. V out is equal to V in because of the short. And at F tends towards infinity, inductor behaves like an open circuit. And so V out is blocked. Sorry, V in is blocked. V out goes towards 0. So this works like a low pass circuit. Low frequencies are passed through. High frequencies are blocked. The transfer function for this filter, because it's low pass, comes out to be the same as the RC low pass circuit, okay? So it is 1 over 1 plus JF over FB. But the value for FB depends on the components, hence the equation is different. R over 2 pi L. This is not the same as the one that we saw for tau in chapter 4. Okay, this is R over 2 pi L. The cutoff frequency or the break frequency is R divided by 2 pi L. Okay. Then if you take the output across the inductor, same circuit, it behaves the exact opposite, becomes a high pass circuit. When f tends towards infinity, inductor behaves like an open. High frequencies are passed through. And you obtain output. Therefore, it is a high pass filter. A high pass filter. It's the same RL circuit, no difference. Series connection of resistor and inductor. If you take the output across the inductor, it behaves as a high pass filter. If you take the output across the resistor, it is a low pass filter. Okay. When I say it behaves like, it doesn't mean the behavior changes. It's the same behavior. If you want a high pass filter, you take the output across the inductor. If you wish to use it as a low pass filter, then you take the output across the resistor. That's what it actually means. Okay. All right, questions. I think there's a ton of new information here. So I will say we will end class here today. Okay. End class here today. Quiz on Monday most likely will be on chapter 5, AC analysis, again, based on examples 1 through 5. Again, I will post the announcement later this afternoon. Office hours today from 2:30 to 4. 2:30 to 4. I have this workshop seminar that I'm attending, so I have to postpone the office hours a little bit later, but I will be available. So from 2:30 to 4. Okay. If you have questions, I'm still around here until my next section begins. Otherwise, I will bid you a good weekend, and I will see you all on Monday. Don't wait to get started on that homework, the one that's due tonight. Again, as I said, it's only 2 questions. One is a short answer question. The other one is the same exact example. Since you already did it now in class, go ahead and knock it out.